Okay, we are seeing a really fascinating shift happening in artificial intelligence. It's no longer just about AI learning from physics data, spotting patterns. Now, we're seeing a whole new generation of AI being fundamentally rebuilt from the ground up to actually think in the language of physics itself.
But that, of course, begs a huge question. Can an AI truly understand the laws of our universe? I mean, not just mimic them, but really internalize them. For years, this has been a major roadblock. Getting an AI to respect something as absolute as, say, the conservation of mass or momentum, well, that's proven to be an incredibly tough nut to crack.
So here's how we're going to break it all down. First, we'll look at how AI and physics even got together in the first place. Then we'll pinpoint the big problem that's been holding things back. After that, we'll dive into two brilliant new solutions, one using smarter math, the other using a totally revolutionary new architecture. And finally, we'll check out the results and talk about what this all means for the future.
Right, so the ultimate dream here is to create what's called a digital twin of the real world. Just imagine an AI that could perfectly simulate the crazy complex airflow over a new jet wing, or predict weather patterns with spot-on accuracy, or even model the plasma swirling inside a fusion reactor. This isn't just about making better guesses. It's about creating this virtual sandbox where we can test and innovate in ways that are just impossible in the real world. That's the dream that's driving this entire field.
And the first big breakthrough toward that dream was something called the Physics-Informed Neural Network, or PIN for short. The idea is actually pretty simple but really powerful. You take a normal neural network and you inform it about physics. So while it's training, you basically add a penalty every single time its prediction violates a known physical law, like the famous Navier-Stokes equations for fluid dynamics. And look, PINs were a huge step forward, for sure. But they have this one fundamental weakness. Because they're just being penalized for breaking the rules, they never really learn to obey them, unconditionally. It's kind of like teaching a kid not to touch a hot stove just by saying ouch every time they do it. Sure, they might learn to avoid it, but they don't fundamentally understand why it's a bad idea. And this all comes down to a problem of constraints. This explains the two approaches perfectly. Standard PINs use what are called soft constraints. Think of this like a penalty fee. The AI can break the laws of physics, but it has to pay a price every time it does. The new goal, though, is hard constraints. This is more like a train on a track. The AI is built in such a way that it is structurally impossible for it to violate the laws of physics. It literally cannot go off the rail.
So how do we build that train on a track? Well, the first approach we're going to look at tackles the problem with just better math. It's a hybrid model called the CAN-PIN. That stands for Coupled Automatic Numerical Pin. It all comes down to how the AI calculates the really complex derivatives that are the absolute backbone of physics equations.
So, traditionally, AIs have used two different methods. You've got automatic differentiation, or AD. It's perfectly precise, like following a recipe to the letter. But it can be slow and really data-hungry. On the other side, you have numerical differentiation, or ND. This one's fast and efficient, more like tasting a dish and guessing the ingredients. It's a great approximation, but it's not perfectly accurate. It's that classic trade-off, right? Precision versus speed. What the CAN-PIN method does is so clever. It just combines the two. It takes the precision of AD and blends it with the efficiency of ND. And what you get is this hybrid model that has the best of both worlds. It's super accurate, it's robust, and it can learn from way less data, which, for these kinds of complex problems, is a massive, massive advantage. Okay, but what if we could go even further? I mean, what if instead of just making the math better, we could redesign the AI's entire architecture to have physics baked right into its very core? Well, that is the revolutionary idea behind our second solution, the Riemann Tensor Neural Network, or RTNN.
This quote from the researchers really just hits the nail on the head. They are encoding the structure of the physics, the partial differential equations, at the network level. See, this isn't about penalizing bad behavior anymore. This is about building an AI that can only behave in ways that are physically consistent.
So how on earth do they do that? Well, the secret sauce is a mathematical concept called divergence-free symmetric tensors. I know, it sounds super complicated, but just think of them as the perfect Lego blocks for building physical systems. The divergence-free part is the key. In physics, that property is directly linked to conservation laws. So by building a network out of these special tensor blocks, you're not just telling the AI to conserve mass and momentum, you're building it from components that make it physically impossible not to.
All right, so we've got two really promising new approaches, one with smarter math and one with a brand new architecture. But do they actually work? Let's take a look at the results, because the proof here is, well, it's literally in the pictures.
Okay, check this out. This first test is a simulation of a really complex vortex. The vertical axis is the error, so lower is way better. That blue line, that's our new RTNN model. Just watch it plummet. It drops orders of magnitude below the standard pin, which is the green line, and another model, NCL, in red. I mean, the difference is just staggering. And if the graph wasn't convincing enough, just look at the raw numbers. The RTNN gets an error rate of 9.9 times 10 to the minus 5. Now compare that to the standard pin. Its error is about 400 times higher, and the NCL model, that's almost 4,000 times higher. This is not a small improvement, people. This is a monumental leap in accuracy.
And now you can see that exact same difference visually. These are error maps, so brighter colors mean more error. The RTNN on the left is almost completely dark, which means its predictions are incredibly close to the real thing. The standard pin on the right, though, look at all those bright yellow zones. That's showing you exactly where it's making huge mistakes trying to model that vortex.
Let's look at another test. This one's simulating the incredibly complex wake of air flowing past a cylinder. On the left is the ground truth. In the middle, the error map for the RTNN is almost perfectly dark, a super accurate simulation. But on the right, the NCL model is just lit up with error, showing it really struggled to capture those complex dynamics. And one last example, from an even tougher field, magno-hydrodynamics, which is this wild combination of fluid dynamics and electromagnetism. And guess what? The pattern holds. The RTN error map there in the center is dramatically darker and cleaner than the baseline model on the right. The evidence is it's overwhelming.
So what does this all mean? Let's step back for a second. These advancements aren't just small, incremental improvements. They really represent a fundamental change in how we can use AI to understand and engineer the world all around us.
So to sum it all up, we've gone from an AI that was simply told about the rules of physics to an AI that is literally built from those very rules. We got here through two huge innovations, the smarter hybrid math of CAN-PIN, and even more profoundly, the physics-native architecture of the RTNN. And the result is AI simulators that are just demonstrably orders of magnitude more accurate and way more reliable.
And this is why it matters. This is not just about making better charts for a research paper. Having AI that you can actually trust to obey the laws of physics, that is critical. It's how we're going to design safer and more efficient aircraft. It's how we're going to build more accurate climate models. And honestly, it's how we're going to solve some of the biggest engineering challenges of our time.
And that leaves us with one final, pretty profound thought. Now that we are actually creating AI that can genuinely master the fundamental laws of nature, the possibilities are almost limitless. The only real question left is, what part of our world are we going to simulate next?